Welcome back. Now we are going to derive the equations of motion from their definitions. So that's the only thing we are going to do in this lecture. It will be brief, except that it's a bit loaded. You may have to follow me carefully. Now, the first equation of motion. You are familiar with some of these equations, but I'm just taking you through how we derive them. The first equation is simply the definition for acceleration. If you do remember, we said acceleration is the rate of change of velocity with time. So this is the change of velocity. Final velocity minus the initial velocity gives you the change in velocity divided by the time taken for this change to take place. You just have to rearrange this equation so that you make the final velocity the subject and you get the first equation of motion. That's the final velocity being equal to the initial velocity plus the acceleration multiplied by the time taken. That's all about the first equation of motion. The second equation of motion, you may have to cast your mind back to the video lecture on describing motion. There was one point we said the average velocity can be defined as the total distance covered divided by the time taken. Or alternatively, it can be estimated by summing the initial velocity and the final velocity and divide it by 2. So these are the alternative equation for finding the average velocity. What it means is that we can approximate them together, we can put them together. That's this average velocity here can be substituted. In other words, this d over t is the same as u plus v over 2. That's what we've written here. Remember, we are deriving the second equation of motion. We start from the average speed equations, put them together. We just equate them together. We get this one. We can rearrange them and then get this. Then we come back to take the first equation of motion. We just saw it. This is the first equation of motion. And we substitute it in place of the final velocity. That's instead of v, we are going to put the u plus at and then go through the arithmetics, just the algebra you are very much familiar with. You just have to be expert in handling fractions and expansion and factorization of expressions. You have to master that, and you arrive at the distance covered being equal to the initial velocity multiplied by the time plus the acceleration time squared divided by 2. This will be your second equation of motion. You can appreciate it much better if you go through the steps for deriving it. You may see it as very difficult, but just follow algebra, the algebra that you've learned in your mathematics classes, and then you'll be alright, you'll be able to derive it. So we can move on to the derivation of equation 3. This one is going to be a bit confusing, but again, you just have to master your skills in handling algebra. If you're able to handle fractions and algebra well, you'll be able to do this one so easily with some few tricks that you may have to pay attention to. Alright, for that one also, we start with equation 1. Equation 1, if you do remember, is simply the acceleration, the definition of acceleration. But in the derivation of the third equation, we are only going to make t the subject. So we multiply through by t, so that t, because there is at here, we divide through by a, and a appears here while t is left somewhere here. That's what we are doing here. There. So t is equal to the change in velocity divided by the acceleration. That's the time. Then we put this expression in equation 2. We go back to equation 2 Wherever we find t, we put the expression in terms of t. We put this t there. So ut, this is t, so we put this one there instead of the t there. Then we have t squared here also. We put this there instead of the t. From here, we are left with algebra. What I did here, you may do it in other ways, but you just have to follow algebra, the rules in algebra and how to handle fractions, and you'll be all right. What I did here was to expand this bracket. If I expand it, it is something over another thing. So the first one takes the square. That's u minus v minus u squared. That's what is here. Then the a itself will also carry the square here. The a squared. That's what I've brought here. I've multiplied by the 2 here, and we have 2a squared. There is already acceleration symbol here, a. It's already here. So one of the a will take care of the one of the a down here, and we'll be left with only one a at the denominator on this side of the equation. Now this one will also carry the squared here, and we can expand it. If we do expand this side, we are going to have v squared minus 2uv plus u squared. Go back to your secondary school algebra, and you appreciate this one better. Now when we come to this side also, we have v minus u all over a. We can expand this one by multiplying the uv multiplied by negative u, again multiplying negative u here, we get negative u squared here, or in brackets, and divided by a. We want to have a common denominator, so what we do is we multiply through the whole equation by 2a. So we multiply this term by 2a in order to obtain 2ad here, and when we multiply this one by 2a, the a here, acceleration here cancels the a there, leaving 2. This is the 2. Then later on we are going to expand this one. Okay, then when we come here, we are going to multiply this whole expression by 2a, and that one will take care of the denominator. Everything will vanish from the denominator here. So we've simplified the expression. We have the numerator being left v squared minus 2uv plus u squared. That's what we have here. So the equation is becoming simpler and simpler. Let's expand this one. We expand this one, we get 2vu, and that's what is here, minus 2u squared. That's what is here. We are left with v squared here, and negative minus 2uv also here, plus u squared, which is also written here. This one is negative and this is positive. They are the same thing. Sorry, I should have simplified it better, but we have vu, and it's the same as uv. 3 times 2 is the same as 2 times 3. Commutative property of multiplication. So this 2uv is the same as 2uv, and one of them is negated, so we cancel each other. They are going out, leaving 2ad minus 2u squared plus u squared. This one will leave only one negative u squared here. Then this one will be left there. We just have to rearrange and have v squared being equal to 2ad plus u squared. We can write it better as we are much more familiar with this one. This is an important note I want you to keep in mind. The equations of motion that we've discussed so far are useful for motions in straight lines. Yes, so for circular motions, there are another set of equations. They are similar to these straight line equations, but they are different. So we use this one for objects that are traveling in straight lines. Okay, then the acceleration should also be constant, or it should be uniform. That's when we can use this equation. So if you have a case or a problem that you are solving and the acceleration is not uniform, then the equations of motion may not help you. may have to use the calculus method to solve your problem. But if they are in linear motion, they are traveling in straight lines, and the acceleration is also uniform, predictable, either deceleration negative or acceleration positive. So long as it is uniform or constant, we can use the equations of motion. So that's it for now. Let's summarize all that we've discussed. The equations of motions are here. We just talked about this. It's applicable for linear motion and then when acceleration is also constant. Thank you very much.